All right, welcome everybody. Let's do this. First off, my bad on the previous two videos. I realized I blasted the music, but it's okay. This is like the more important of the lessons. So what I'd like you to do is first, this is the proper definition of a vertical asymptote. What I want you to do is just take your time and copy this down, and then we'll talk about it. Okay? So let's imagine you copied it down, and we're ready to roll. Over here, let's look at we have a vertical asymptote over here at x equals a, but you have to understand that a vertical asymptote will only happen if the limit from the left of a either goes to positive or negative infinity, right, like this one does, or if the right of a, it goes to positive or negative infinity, and that's what happens here, right? You see, to the left of a, it's going to negative infinity. To the right of a, it's going to positive infinity. So based on this definition, you're allowed to say that there's a vertical asymptote. All right? Let's take a look at the next one. Here we have a horizontal asymptote, and this is the proper definition for a horizontal asymptote. What I want you to do is take a second and copy this down. This says the horizontal line y equals b. So in this example over here, when we take a look at this, why is b a horizontal asymptote over here? Because what is happening as the limit of f of x, what happens as it goes to negative infinity? It can never cross this line. We say it's getting close to it, so that's an asymptote. Notice that you have to be going to negative infinity, or the x has to be going to positive infinity for us to create these horizontal asymptotes. So what we're going to do today is we're going to show the proper justifications for vertical and horizontal asymptotes for rational functions. So let's take a look at the next part. Do you remember in the last example in the video when we did this? So what did we accomplish here? How do you find the vertical asymptote, right? What do? We factor the top, we factor the bottom. And when we look at this one, you see at x plus 5, the x plus 5 cancels. But which one does not cancel? It's that x minus 2. And then what did we just say? We just said x equals 2 is a vertical asymptote because it did not cancel out on the top. You see, this is not enough to fully justify why x is equal to 2. We have to use the proper definition of a vertical asymptote to show why there's a vertical asymptote at x equals 2. Just to say that this x minus 2 cancels is not enough. So how do we properly show the justification for this? And it's this idea here. We have to take the limit from the left and the limit from the right of 2. If I take the limit from the left of 2 and take the limit from the right of 2, if this is equal to positive or negative infinity, and if this is positive or negative infinity, then you're allowed to say that 2 is a vertical asymptote. You cannot say that 2 is a vertical asymptote because it doesn't cancel. This is the proper justification. So then how do we do it over here? Well, you just do this. You say the limit as x approaches 2 from the left. And what are we going to do? We're going to evaluate it for this function, for the 2x squared plus 9x minus 5. And x squared plus 3x minus 10. And don't you remember, if you go the left of 2, what is a number left of 2? You could say 1.9. And you know this is a vertical asymptote, but all you have to show that it goes to positive or negative infinity. And what you have to do is you don't have to plug in 1.9 into the whole thing. Notice that you see how it factored and we canceled the x plus 5s, you're allowed to just say that this whole thing is equal to this. So it makes your life very easy. So you're just allowed to just say, okay, this is 2x minus 1, and this is x minus 2. Okay, well, let's see. When I plug in 1.9, what is 2 times 1.9 minus 1 over 1.9 minus 2. Will this be positive or negative? All right, so take a second and think about it. Let's see, on the top, this should be positive, but 1.9 minus 2, that's negative 0.1, so I have a negative here. So this implies that it goes to negative infinity. And it does, according to that graph. Okay, according to that graph, it does go to negative infinity. But you see how we use the definition of vertical asymptote to justify it. Okay, and that's what you guys need to do from now on. You cannot say that 2 isn't a vertical asymptote just because it doesn't cancel. You have to show that the limit as you approach the left goes to one of the infinities, and you also have to show that the limit from the right also goes to the other infinity. So then you could say you have 2x minus 1 over x minus 2. And here, what is a number right of 2? You could say 2.1. And if I plug in 2.1 in here, what is 2 times 2.1 minus 1 over 2.1 minus 1, right? On the top, you get something that's positive. On this top, on the bottom, you also get something that's positive, so it goes to positive infinity. You see, this is the proper justification, all right? Let's take a look at the next one. So we did vertical asymptote. Now, how do we properly justify horizontal asymptote? If you remember before, how did we justify this horizontal asymptote, right? What did we do? If the degree of the numerator was greater than the degree of the denominator, we said no horizontal asymptote, right? If the degree of the numerator is less than the degree of the denominator, we said y equals 0 is the horizontal asymptote. And if they're equal to each other, what do? You take the leading coefficients and you just divide them. So this is just 2 over 1, which is 2. But you are not allowed to do this in calculus. You have to use this definition to properly justify it. And how are we going to do that? So let's take a look over here. If I have, notice that we have to show both sides. You have to say that the limit as x approaches infinity goes to some value. Well, okay, so the limit as x approaches infinity of 2x squared plus 9x minus 5 over x squared plus 3x minus 10. Now, you're not allowed to just plug in infinity, not yet, because it gets a little bit weird. So you're allowed to do an algebra 2 trick, which looks something like this. You divide each term by the highest degree of x in the denominator. Okay, so what I want you to do is take a second and write that out, and we'll go back to it. So what does that mean? If I have divide each term by the highest degree of x in the denominator. So what is the highest degree of x in the denominator? The denominator is 2. So what I'm going to do is I'm going to take this 2x squared plus 9x minus 5 all over x squared plus 3x minus 10, and I'm going to divide each of them by x squared. Okay? I'm going to divide each of them by x squared. Now, you should not just say, oh, Mr. G said I'm allowed to do this, so I can do this. You should think about, wait, Mr. G, pause. Why is it in math we're allowed to just do this little trick? Well, this will only take 1 minute, but let me show you why you're allowed to do this. Let's take a look at this example, okay? Imagine if we just had simple numbers where life is very nice. Imagine if I just said, what's 10 plus 6 minus 4 divided by 12 plus 8 minus 2, okay? Just take a second and just do this, right? So now, what's 10 plus 6? It's 16. 16 minus 4 is 12, okay? And then what's 12 plus 8 is 20. 20 minus 2 is 18. And notice if you simplify this fraction, what's the greatest common factor is 6, right? So divide this by 6, you get 2. Divide this by 6, you get 3, okay? Well, what if I just, for fun, I have the same exact thing, and what I'm going to do is I am going to divide 2 to each one of these, will I somehow still get 2 over 3? Notice, what is dividing 2 over 2? That's the same as 1. And what is, let's say if I have a value of a, is a equal to a divided by 1? Absolutely. If you divide anything by 1 or multiply anything by 1, you get the same value. So let's see if we get the same value of this. Let's just divide everything by 2. If I divide this by 2, divide this by 2, divide this by 2, divide that by 2, you see I'm just dividing everything by the same number. Hopefully we get this at the very end. So let's see, what's 10 divided by 2? 5. 6 divided by 2? 3. This is 2. This is 6. This is 4. This is 1. Okay? And what's 5 plus 3? 8. 8 minus 2 is 6. And then 6 plus 4 is 10. 10 minus 1 is 9. This is 6 over 9, but how do you simplify this? Oh my, wow, it's the same. It's the same. So you're allowed to do that little trick. You're like, wow, Mr. G is going crazy. But all right, so so you're allowed to do this trick of taking each one of these things and dividing it by the same number. So how does that help us here? Okay, let's focus now. All right, I bet you guys are laughing that Mr. G's got jokes. But okay, so here you got limit as x approaches infinity, right? So we still have to do this. Remember, we're not allowed to say this trick. You're not allowed to do that. You have to take the limit to each one of these. So let's see what happens here. Let's do it step by step. What is 2x squared divided by x squared? Notice this just cancels, so I have 2. Okay. What is 9x over x squared, right? This, take your time and try and do this by yourself, but this should just be 9 over x, okay? Because notice if I have 9x over x squared, that's the same as 9x over x times x, and what happens is one of the x's cancel, so I'm just left with 9 over x. So this is just 9 over x, okay? And then this one, you can't really do anything to it, so it's just minus 5 over x squared. And we're still also taking the limit as x approaches infinity, okay? Well, take your time and try and do this one by yourself, right? Pause the video and try and do this. But notice what's x squared divided by x squared is 1. What's 3x divided by x squared? Okay, so 3x divided by x squared, that's 3x over x times x, that's just 3x. I'm sorry, 3 over x, right? Because these x's cancel, okay? So this is just 3 over x. And then this is minus 10 over x squared. You can't really do anything. But the next thing I think you remember seeing is, where did I put this? Ah, yeah, it's over here. Now, let's take a look at this. Here, you want to take the limit as x approaches infinity. But you have to understand that you can't do anything to that. But what happens if you take something like 9 over x or like 1 over x? Why is it that when you take the limit as x approaches infinity for this or something like this, it has to equal 0? And the idea is, imagine if you have, I got you. Let's say if you have the limit as x approaches infinity for 9 over x. Well, let's just think about it. Imagine if you have 1, then 2, then 3, then 4, then 5, then like a million, right? Imagine if you have 9 over 1, 9 over 2, 9 over 3, 9 over 4, 9 over a million, right? Notice that as this is going to infinity, right, this value is getting very close to 0 because the number, you see, when the value of the denominator gets bigger, the value gets smaller. So you have to think as this number gets very, very big, the whole value of the whole thing is getting very small and it's going to 0. And that's that idea over here too, that this just becomes 0. This one becomes 0 as x is going to infinity. And this one too, this is 0. And this is 0. And then all we're left with is just 2 plus 0 minus 0 over 1 plus 0 minus 0, but that's just 2 over 1, which is 2. And that's it. But what does this 2 represent? Take your time, pause the video. What does this 2 represent? That represents y equals 2, which is a horizontal asymptote for this function. Okay? And don't you remember if we did the trick? What was the trick? You just did the same thing. You just did, they have the same degree, right? It's 2 over 1. But this is a pre-calc algebra trick. You're not allowed to use that trick in calculus. You have to show with justification that when you take the limit of it, it's going to some value. And notice that this satisfies the definition from the beginning. It's saying as you take it to infinity, show that it goes to a number. And the same thing will happen if you do it to negative infinity, and we don't need to do it because imagine if this just said negative infinity. Okay? Well, let's say if I say, for example, we're almost done because I realize this is a long video. Because imagine if I have 9 over x and x is going to negative infinity, right? Okay, that's really weird, my bad. Limit as x approaches negative infinity of 9 over x, right? This is the same idea because if I have 9 over negative 1, 9 over negative 2, 9 over negative 3, this value becomes negative, but it's a negative 0, or like it's a negative times 0 because this value just gets very, very small. So it won't make a difference if it was positive or negative infinity. But that's it. And we showed that the horizontal asymptote is 2. Okay? So what's the recap? Basically, first move. Take a second and just rewind. What did we do? Okay? Vertical asymptote. Let's just really quickly review. Okay? To properly justify vertical asymptote, you found that one of them didn't cancel, but that's not enough. What do you have to do? You know 2 is the vertical asymptote, but you have to take the limit from the left and the right to satisfy the definition. That when you do the left and from the right, you have to show that it goes to one of the positive or negative infinities. For the horizontal asymptote, you have to play this little game of taking it to the infinity and then dividing each term by the highest degree of x in the denominator. And I forgot to give a shout out to Senor Frank because he said, Mister, why did you divide that by x squared? And he also asked, why are you allowed to do that? And I gave you a little justification. So shout out to Frank for the great question. And yeah, that's what you need to do. What I want you to do is take these previous examples you've done before, right? G of x and h of x. You already found the vertical and the horizontal for each of these. But what I want you to do is show it doing the proper justification for each one of them, okay? And what I also want you to do is try and practice this. And this will be your homework for tonight. What I want you to do is find all vertical and horizontal asymptotes for these functions and justify your findings using limits, okay? You cannot justify with tricks. You have to show with limits. All right, who's getting that 5? I'll see you.